Okay, we're going to talk about rational functions today. Um, so, starting chapter 4, we're going to learn, we're going to talk about the domain and range of these rational functions. We're going to find some asymptotes, both horizontal and vertical, and we're going to solve real-world problems with these. So, let's talk about the domain first. This is our standard hyperbola. This is f of x equals 1 over x. Okay, it's our standard rational function, 1 over x. Let's find the domain in this, and let's look at the behavior as x gets really big and as x gets really small. And let's look at any x values we can't have as well. So go ahead and try to find the domain and talk about the end behavior of this function and any restrictions on x. Go ahead. Okay, so if you take a look at this graph, if you get it graphed and look at it, you can see that it's a hyperbola here. And from looking at it, it looks like it has horizontal asymptote at x with y 0, and a vertical asymptote with x equals 0. So we know the two asymptotes just by looking at it. The domain is then all real numbers, but x can't be 0. So we would say that, I'm going to use interval notation. So I'm going to say negative infinity all the way to 0, but not including 0. And then 0 all the way to positive infinity. So there's interval notation for the domain. This means all real numbers, but x can't be 0. All right. Now the behavior of f near any excluded x values. So let's look at a couple other things though. Let's talk about end behavior. Okay. End behavior of this function would be as x goes to positive infinity. So as x gets really big, the function value or the y value goes to 0. Okay? As x gets really big, the y value goes to 0. As x gets really small, as x goes to negative infinity, the y value also goes to 0. So there's some end behavior about what happens when we go way to the right and way to the left. Now let's look at what happens as we get near our asymptote right here. So as x approaches 0 from the left, let's say. So as x approaches 0 from the left, that's what this little minus sign up top means. The function value approaches negative infinity. So I'll write this as asymptote behavior. All right. As x goes to 0 from the left, the function goes down to negative infinity. As x goes to 0 from the right, the function goes to positive infinity. All right, so to summarize this information, when you have vertical and horizontal asymptotes, the line x equals a is going to be our vertical asymptote. And basically, that's when the y value goes to infinity or negative infinity. Okay, as x approaches that value. All right, and the line y equals b is going to be our horizontal asymptote. So y equals number is always our horizontal line, and y is going to approach that number, whatever that number is, as x goes to infinity or negative infinity. So let's just look at some functions then. Here's the function 2x plus 1 over x plus 1. Okay? It's got a vertical asymptote at x equals negative 1 and a horizontal asymptote at y equals 2. Okay? So you can see that as x goes to infinity, the y value of this function goes to 2. Okay? As x goes to negative infinity, the y value for this function goes to 2. Okay, that's exactly what this just said. Whoops. Right here. Okay, our horizontal asymptote, y goes to 2 as x went to infinity and negative infinity for this example right here. Okay, so you don't need to know this notation necessarily. What I do need you to realize is that this is a vertical asymptote. It's at x equals negative 1. This is a horizontal asymptote, and I'm going to show you how to find those in a second. But here's another example. this function 4 over x squared plus 1, it's got a horizontal asymptote y equals 0 right here. So as x goes to positive infinity, the function goes down to 0. Same thing with negative infinity. Here's another function. This one has a vertical and horizontal asymptote. The vertical asymptote is at x equals 1. The horizontal asymptote is at y equals 0. Okay, let's look at how to find some of these. Okay, let's find the vertical and horizontal asymptote for, well, this one I've already given you. The vertical asymptote for this one is x equals 0. Horizontal asymptote is y equals 0. This is the function we just looked at. Okay. All right, so here's how we find horizontal and vertical asymptotes. This information might seem confusing, but I put it on your formula sheet for you. So basically, it tells you that the vertical asymptotes are at the zeros. So that's at the places where the denominator is 0. And the horizontal asymptotes, it depends. If the exponent's higher in the bottom than the top, then y equals 0 is the horizontal asymptote. If the exponent's the same, then the asymptote, the horizontal asymptote, is the ratio of the leading coefficients. And if the exponent's higher in the top than the bottom, then the graph has no horizontal asymptote. So I know that's a little bit tricky to remember at first, so what I did is I put it on your formula sheet for you. It's right here. I put it in simple English, so when you're trying to find a horizontal asymptote, if you have the same exponent in the numerator and the denominator, then the asymptote is a fraction of the leading coefficients. If the exponent's higher in the bottom, then the asymptote is the line y equals 0. And if it's higher in the top, then there's no asymptote. Okay? And you don't have to worry about this end behavior asymptote yet. I don't know if we'll get to that. But basically, we can also find an oblique asymptote, an asymptote that's not necessarily vertical or horizontal. We'll call that an end behavior asymptote. I'll talk about that if it comes up. And then the vertical asymptotes, like I said, occur at zeros in the denominator. All right, so let's look at an example then here. I want you guys pause this and try it, but I want you to find vertical and horizontal asymptotes of the graphs of both of these functions. So find any vertical and horizontal asymptotes for these. All right, you should get these answers. Let me explain. For the first one, this is 2x over 3x squared plus 1. How I find horizontal asymptotes, once again, this is on your formula sheet. If the exponent is the same in the numerator and denominator, then the asymptote's a fraction of the leading coefficients. That's not the case. But if the exponent's higher in the bottom, which it is in this one, the exponent's higher in the bottom, that means the horizontal asymptote is the line y equals 0. Okay? Because it makes sense too. This function, whatever it looks like, as x gets bigger, it's getting bigger in the bottom faster. So if it's getting bigger in the bottom, then you can tell that the values are going to get smaller and smaller as x gets bigger and bigger. Think about it. You know, you have 1/2, and so you have like 2/6, so you have like 3/9. You know what I mean? As this number gets bigger faster in the bottom of any fraction, you can see that the value is going down overall. Okay? So, horizontal is y equals 0. Now, the vertical asymptotes occur as zeros in the denominator. So what I would want to do is take the denominator and set that equal and find out if I can get any zeros in the denominator. Subtract 1 from both sides. Divide both sides by 3. Square root both sides. No, I get imaginary zeros. So there are no real zeros to the bottom, therefore there are no vertical asymptotes for this one. Okay? And you can graph it on your calculator to make sure. All right, you can see this function. This is a little bit different, but the function looks like this. It doesn't have any vertical asymptotes. It does have horizontal asymptote though at y equals 0. You can see that the function approaches y equals 0 as x gets big, and the function approaches y equals 0 as x gets really small. Okay. All right, let's try another one then. B. For B, the horizontal asymptote, since the exponent's the same in the top and the bottom, then the asymptote is the line y equals, and you take the fraction of the leading coefficient, so that's 2 over 1. So it's y equals 2. So the leading coefficients are 2 and 1 if it's in standard form. So it's 2 over 1, which is 2. This is a horizontal asymptote. The vertical asymptote occurs at zeros in the denominator, which there are 2 of them. X equals 1 and x equals negative 1. Right? If you take x squared minus 1, you set equal to 0. You add 1 to both sides. And then you square root both sides. You get x equals plus or minus 1. So these are the two vertical asymptotes. All right, now let's check the graph to make sure that we get the same result. All right, so if you take a look at this graph, then you find out that what we got was right. It does have a horizontal asymptote at y equals 2, which is this red line right here. Okay? And then it does have two horizontal asymptotes, one right here at -1, and one right here at +1. So if you use these rules right here, I couldn't have made this any easier for you. This is almost not even fair. I mean, I don't want to make it too easy for you because when you take your CLEP test, I want you to try to memorize this stuff. That's why if I were you, I would make note cards for this stuff. The things I put on the formula sheet are things that, you know, are a little bit more difficult to remember. So if I were you, I'd make note cards for this stuff. It's not that much. You need maybe like 5 note cards or something. 1 note card for lines. I don't know, 1 note card for the sum of difference of cubes. 1 note card for the distance and midpoint formula. 1 note card for the equation of a circle. And there's not that much stuff to remember. 1 note card for parabola stuff. And then 1 note card for horizontal and vertical asymptotes. All right, let's try one more problem. It's an application problem. This function right here is a rational function, and it's cost in terms of P, where P is the percentage of the smokestack pollutants for this company. So P obviously can be between 0 and 100, the domain, because you can't have higher than 100% or lower than 0%. So our percentage is somewhere between 0 and 100, and the cost then depends on that pollutant percentage. If we want to get rid of more pollutants, it's going to cost more money. Okay, so sketch graph this function, and then answer the question, if we change the rate or the percentage from 85 to 90%, how much additional cost would that be? So currently, it's 85% the state law requires. If we go to 90%, so we can advertise that our company does this, you know, we're environmentally friendly, how much additional cost would that be? Let's go ahead and try to answer this real quick. All right, so if you look at this rational function right here, we can graph it to get a better look at it. I graphed it here. This is actually, it does have an asymptote, and that asymptote is obviously at 100 because we can't have anything bigger. The vertical asymptotes occur at zeros in the denominator, and the 0 in the denominator is 100. So this function, it approaches 100, you know, as the percentage approaches 100, the cost goes up exponentially. All right, so obviously we're paying a lot more to increase the percentage that we get rid of pollutants in this later branch here. At the beginning stages, the cost is pretty minimal to increase a percentage point, but later, as you get up higher than 90% in this range, you can tell the cost is going to be quite a bit different. So all it asks us to do is find the cost difference from 85 to 90%. So what I did, the easiest way to do this for me, I took the calculator, did second calculate value at 85%, and find out how much it costs to have 85% of the pollutants gone, and that'd be 453,333. 0.33. And then 90% if I got rid of 90% of the pollutants, that would be second calculate value for 90. And that gives you 720,000. All right. So all I did was plug in 0.85 for P and 85 for P and 90 for P and get these two different Y values. All right. And now to find the cost, you just take the difference, which ends up giving you 266,000. I believe 0.6 repeating it, obviously. So. Take the bigger one minus the smaller one. That's how much more it would cost to increase my percentage of pollutants that are removed. Okay, hope this helps. We'll make a homework help video next.